Alright, welcome everyone. In this video, I'm going to be taking a look at a little more of a specialized case for two-dimensional motion. We're going to see, using the equations of motion, right, those kinematic equations from a previous video, we're going to see how an object's trajectory through space is parabolic in nature, and it's dependent upon space, right? No longer time. And then we're going to take that to its conclusion by showing you what's called the range equation, right? And what specific instances that's allowed to be used. Okay, so to start off, let's draw a quick grid here. And so an object, let's say, is launched with some initial speed, v naught, we'll give it a value of 10 meters per second, okay? Somewhat quick, at an initial angle of 60 degrees, okay? So hopefully you've read the chapter and you should know by now that the path or the shape that an object takes through the air is parabolic, right? I covered that in a previous video. We'll cover that a little in a different way in this video. So that being said, before I get into the equations, I need to write out the components. So this is v naught y and v naught x. Whoops. V naught x, okay? And so that initial speed, there we go, is such that the y component will decrease, right, up to a minimum at 0. And that minimum is at this maximum height we'll call capital H, right? And that's because there's a force in the y direction of, well, the gravitational force. And the rate that that component will change, the rate that this v naught y vector will change is little g, right? Minus 9.81 meters per second squared. There is no force horizontally, and so v naught x will not change. That will stay constant the entire way through. Okay, so for starters, what if you wanted to find the time to the top? Okay, how would you do that? Well, actually I should put x and y. How would you do that? Well, if you knew the magnitude of v naught and the initial angle, you could use this equation. Actually, let's do minus g. Minus gt, okay? And so solving that for time gives us v minus v naught y over negative g. The final speed, vy, at the apex is 0, right? The final vertical speed is 0. Also, we can write out v naught y into its constituent component, right? Let's do it, I don't know, v naught y is up there. So that's the magnitude v naught times sine of the angle. All right, and so now we know everything here, right, as stated in the problem. And so if you were to plug those numbers in, you should get positive 0.9 seconds, okay? So that would be the time, say, to t1. What would be the time to go up and come back down to t2? Down here at the ground, the same level that it was launched at. Well, you could use other kinematic equations, right, to piece it through and eventually solve for it. Or you could just reason that, well, going from launch height up to t1 takes the same amount of delta y, right, capital H, and the same time as going from capital H back down to the launch height. Thus, the gravitational force has the same amount of time to act on the object changing its vertical speed. And so the time will be the same to go up as to come back down. And so t2 is simply twice t1. Okay? The real question here, and the point of this video, is what if you wanted to find a time, or what if you wanted to find a final height of some point in between? Right? Say right there. How would you do that? Well, how would you do that? That's at a height we'll call lowercase h, right? To do that, we need to convert the equation y equals y naught plus v naught yt minus 1/2 gt squared. We need to convert this from a function of time into a function of x. Okay, so how do we do that? Well, again, it's the same time to go up to the apex and then back down to that height as it takes the object to go purely horizontally, right? And it's that independence of x and y that's critical here, okay? Yes, the object actually travels, of course, like this, but if you were to picture the components, right, going up and back down, takes the same time as to go like that. And so this equation, as I've written here, is in the y direction. We need another equation. How about the x direction? This would give us the final horizontal position, or the horizontal distance in that time. Okay? So this time here is the same as that time and that time. And because of that, we can solve one of these equations for an expression for time and plug it into the other. So I'm going to do that for this more simple equation. And I'm converting v naught x, by the way. Let's assume that x naught, right, the initial position is 0. And so we get the following expression right there. So now I'm going to take this and plug it in for t. Excuse me. Right there. When we do that, can you see what's going to happen? This will no longer be an equation for time, but rather x. So plug in time, we get split up v naught y, that's v naught times sine theta. Then we have x divided by v naught cosine theta minus 1/2, let's do g over 2 times this expression but squared. Okay, and so now this is a function of x. And again, we can do this because it's the same time in both axes, right, in both dimensions. So here, the v naughts go away, and sine over cosine is tangent, so I'm going to put x before tangent, and then subtracting, whoops, I didn't write squared, subtracting the last term. V naught squared, cosine squared. Okay, this is not the range equation, but this is simply an equation for the vertical height in terms of the horizontal distance, just in case you don't have a time, right? And you did know, say, the horizontal distance, you could find the final vertical height, right? To find time t3, right, we would need to solve or know a horizontal distance, okay? Plug that in here, solve for a time value, then do what I just did and plug it in here, right, to find vertical height. Right. All right, so let's see. This equation here, y of x, is very handy for the specific instance of if you need to find a final height and you only know, horizontal position, theta, v naught, stuff like that. Okay. The range equation is a specific instance of this. Okay. Namely, what's the total horizontal distance right there? What's that? So I don't know if I have room to do it. What's that? What's that range? Capital R. Okay. Well, that range is simply taken by this equation. X equals x naught plus v naught x t. So let's go to the next slide where I have a little bit more room. Okay. And I'm going to show you what the range is. So I'm going to expand out that v naught x. That's v naught cosine times time. And so that range is basically, well, it's basically that, right? It's the final horizontal distance. If the initial horizontal distance started at 0, which it typically does, x is the same thing as r, right? Some books, including your book, use capital R specifically for range. Oops, yeah, cosine theta times time, okay? And so this is the distance, but what if you don't know time? Well, the equation for time can be obtained using, where was it? That equation there. Because remember, we were solving for the time back down to t2, and it was just simply twice what I just boxed. So plugging that in, it was twice, what was that? V naught sine theta over g. The minuses canceled out there. So if we simplify this a little bit, we have v naught squared, well, 2 v naught squared sine times cosine. All right. And this is the range equation, but also if you want to use the trig identity, you can. I don't expect you to know this. I didn't. So if we use that, then this range equation is simply the initial speed squared. Notice it's not in component form. It's the general speed times sine of twice the initial angle over g. This is the range equation, and it's only applicable, right? Only can be used when delta y is 0. Okay? Delta y is 0. What do I mean? I mean, well, it was launched and it came back down and landed at the same height it was launched at. Okay? It's not applicable in instances like this. Not like that. Okay? So, real quick to finish up, what's the maximum range? What angle would give you the maximum range for some initial speed? Excuse me. Well, we need to maximize sine in that case. Sine is maximum when theta is 90. So that means to get that, our argument here to be 90, theta has to be 45. Because sine of 2 times 45, sine of 90 is 0. Sorry. Yeah. 0 is 1. Sine goes away. Sine would be 1. So the maximum range would be v naught squared over g when theta is 45. Okay. The minimum range is when, well, theta is 90. Because sine of 2 times 90 is 180. Sine of 180 is 0, and the whole range is 0. Okay? So I hope you enjoyed how I'm going to get the range equation, as well as the very useful y as a function of x, right? And again, this shows that an object's trajectory through space is parabolic in terms of x. Thanks for watching.